many of you had requested the mock coding interview with Striver. His SD sheet has reached millions of people, and the mock coding interview series would just be incomplete without a mock coding interview with him. I'm pretty sure all of you are going to get to learn so much today. But before we get started, just a quick thing, if you're someone who struggles with consistency or are looking for a structured path or right mentorship, then you can check out the platform Bosscoder Academy. Bosscoder Academy is an online platform which has helped 1,000 plus learners upskill themselves. They have a structured curriculum in DSA, system design, and full stack development for software engineers who wish to crack product based companies. They have live classes, one-to-one mentorship, doubt clearing session, placement support, and for the live classes, the recordings are available if you can't attend live. You can receive mentorship and take mock interviews with boss coder mentors, and they also provide doubt support. They also have a community on Discord. They also provide placement assistance and stats, and they have a 14 days refund policy. So if you are looking for structured program and mentorship, check out the link in the description box. The 14 days refund policy just makes it more worth it checking out. Hi Striver, thank you so much for coming and doing this. You have no idea the number of requests I have gotten for this mock interview. I am sure this is going to be very, very helpful for so many students. Without wasting any time, let's get started. This is your question. Just look at the question and let me know if you have any doubts or questions.
Okay, given an undirected graph with n nodes and m edges where each edge has undirected, okay, n nodes, m edges, cool, where each edge has a weight wi. Find the minimum number of edges that needs to be removed to disconnect the graph into exactly k connected components. Okay, first question. What if the graph already has more than k connected components?
You can assume that k is somewhere between 1 and n.
My question was, what if the graph already has more than k connected components? Imagine you give k as 5 and the graph already has, let's say, 6 connected components. In that case, I cannot disconnect the graph. I have to somewhere connect the graph. So probably the answer for that, shall I print -1 or what?
Okay, print -1.
Okay, so if any case we have more than k connected components, we go ahead and print -1. Okay, minimum number of edges is what you are looking for into exactly k connected components. Cool, give me a second. Okay, if I remove something which is a cycle, that will not break it down into multiple components. So I cannot remove something which is a cycle. I need to remove something which disconnects it completely. K connected components. K bana dega. Or if I give you a graph like 1, 2, 3, 4, 5, 6, 7. K is in the range of
1 to n, both inclusive.
What is the constraints for n?
You can assume within integer limits.
Within integer like 10 to the power 9?
Like, let's say if you can fix the algorithm in that much. No, nothing is given.
N 10 to the power 9, like that will be impossible to solve, right? Because if n is 10 to the power 9, you can't take the inputs of the graph.
Okay, let's go ahead and see what algorithm you can come up with, and then we'll see the constants.
Okay. Okay, I think I got an algorithm. So, assuming you are giving me edges and I have to form the graph. So, what I'll do is, while forming the graph, I'll keep connecting the edges and I'll keep a track of the edges on whose connection we form a new component. Sorry, we form I'll keep a track of those edges where you connect two nodes and you connect two separate components into one. Okay, So I'll keep a track of the number of such edges. So I'll give you a example. For example, imagine you have a graph something like 1, 2, 3, and 4. So this is the graph, and we have 5, 6, 7. Okay, and imagine 8 is connected to 5. Okay, so over here, something that we can see is, even if you take this edge 8, 5, even if you remove this, it will still does, like, it's still a cyclic stuff, like 5, 6, 7, 8, 5. That's a cyclic stuff. So even if you remove the edge between 8 and 5, it won't break it down into multiple components, correct?
Right.
So what I'll do is, I know over here, if you remove any of the edges, the 1, 2, 3, 4, if you remove, let's say, between 1, 2, that breaks it down into multiple components. If you remove 2 and 3, it breaks it down into multiple components. If you remove 3 and 4, it breaks it down into multiple components. So what I'll do is, I'll keep a track of which are such edges on whose removal I end up getting multiple components. Like, for an example, with the example that I gave you, the edges will be 1, 2, 2, 3, and 3, 4, on whose removal you can get multiple components, correct? And similarly, on the other one, it will be 5, 6, 6, 7, 7, 8, not 8, 5, because on removal of 8, 5, you don't get separate components. So I'll just go ahead and count those number of edges so that I know. And what I'll do is, I'll also count how many current components you have. Okay, so imagine X is the number of components the graph already has. Okay, and you're looking for K. That's your target that you want to achieve. So the number of new components that you want to form is definitely K minus X, correct? You want to form something like K minus X. So if I have to give you an example, so on breaking out, like, if you take up any, like, if you just remove any of the edges, it basically introduces a new component. If you understand that correctly, like, if I remove 1 and 2, that will split it down into one new component, because this is a component. The moment I split 1 and 2, it basically gives me one more component. So if the number of such edges is, so basically the answer is K minus X, and that is only possible if the number of individual edges is greater than equal to K minus X. So the answer will be K and X, where X is the number of components. Yeah, that's going to be my answer for this one.
Okay, so this number that you're storing, is it same as the number of edges that would form cycles? Like in your case, you said 8, 5, right?
Yeah.
So that is the edge that led to cycle. So that is basically what you're trying to find initially.
No, I'll just keep a track of the edges on whose removal we split into different components. So basically, when you try to connect 8 and 5, what you will see is 8 and 5 are already connected, correct? 8 and 5 are, I'm not sure if you can see the highlight that I'm doing. Are you able to see the highlight?
I can.
Yeah,
yes,
so the moment you try to connect 8 and 5, that's already connected. So even if you remove that edge, that's of no use because it's still in the component. So I'm trying to figure out the edges on whose removal there is absolutely, like, it will definitely split it into two components.
Okay. So just like, it's just something that I wanted to understand. Like in this case, in the example that you've taken, 8, 5 is also leading to a cycle. So will it always mean that those edges are the ones that are leading to cycles?
I did not understand your question.
Like 5, 6, 7, 8, there was no cycle, right, in that component. As soon as you add 8, 5, there's a cycle. And 8, 5 is also the edge that was like on deleting which you were not getting like a different component.
Yes.
So are the two things same, or like, is that what you're trying to find?
No, I'm just trying to find out which edges on removal will give me two separate components. So 8, 5 is not something which I'm wanting to find. I'm wanting to find 1, 2, 2, 3, 3, 4, 5, 6, 6, 7, 7, 8. So these are the edges that I'm trying to find, because any of these edges on removal will help me in getting that. And on the contrary, I can say that if you have removed 5, 6, then this is something if you remove 5, 6, what will happen is it is still a part of the component. So you have to kind of be careful about these things. That, like for an example, even if you remove 6 and 7, it will still be a part of that cycle. So what we need to find is the components which doesn't have any edge which still connects it. I hope you understand what I'm trying to mean. Like you have to kind of find out the components where there's absolutely no cycles. That's one of the things that you have to find out. And if I can figure out the number of edges, I think the answer is pretty straightforward. Current components, which is x and k, is your required. So I'm sure that the number of edges that I have to remove at minimal might be k minus x.
Okay, for the graph that you have taken, say k is 3. So what is your x and what is your answer?
If your k is 3,
yeah,
if you just remove 1 and 2, one of the edges, that will be your answer. Because currently we have 2 components, right? And you're saying we have 3 as the answer. 3 is what you require. So if you remove the edge between 1 and 2, you'll be able to get the answer. So x is the current number of components, which is 2, and k is the required that you wish. So if you just remove 1, which is 3 minus 2, you actually get your answer. Yeah.
Okay. Can you tell me the algorithm and what is the time complexity of the algo that you're planning?
What we can do is, okay, what can we use? We can go ahead and probably use, what are we trying to keep a track? We're trying to keep a track of the number of components. And we know k is what we are looking for. Okay, k is what we are looking for. Can you give me a second? I am trying to figure out an edge case. Three minutes and k is 3. मैं ये वाला केस लेता हूँ, पूरा साइकिल है, k3 है, ये कंपोनेंट है, आंसर दो है, आंसर दो नहीं है, आंसर तुम्हारा दो हो ही नहीं सकता, क्योंकि आंसर तुम्हारा होना पड़ेगा 3 edges, which is hypothetically correct. If I can remove the cycled part which connects it, that is what will make sense. Okay, so I figured out an edge case. So take this case where 1 is connected to 2, 2 is connected to 3, and k is 3. Okay, so over here, x, which is the current number of components, is 1. K is, assume 3, which you want to achieve, and the answer will not be 2. Sorry, if you connect this, the answer will not be 2. Why am I saying that? You can remove any of the 2, like even if you remove 1, 2, 2, 3 still stays connected. And even if you remove like any of one edge, if you try to remove 2 edges, we will just get 2 components, which is like 1 and 2, 3 connected, right? So I think we have to consider the case of cycles over here. That's the edge case that we have to deal with. If we can consider the case of cycles, I think we should be able to do it. And in order to consider cycles,
also, Striver, note that you are given minimum number of edges. What is what you have to find?
Yeah, correct.
Just keep that in mind.
जब साइकिल कनेक्ट करा अगर मैं उसको हटा दूँ तो मेरे काम हो जाएंगे, तो मुझे नॉन साइकिल एजेस गिनने पड़ेंगे. ओके, एक कंपोनेंट जिसमें नॉन साइकिल एजेस कितने हैं, अगर मैं वो गिन लूँ तो मेरे काम हो जाएगा. ठीक है, इफ आई कैन जस्ट फिगर आउट which component has a cycle, that's what I have to figure out. That's it, everything should be done. Number of cycle, कितने एजेस साइकिल बना रहे हो वो तो गिनना पड़ेगा. अगर कितने एजेस, हाउ मेनी एजेस ऑफ फॉर्मिंग साइकिल्स, फैक्टर ऑन दैट, तो वो साइकिल्स मुझे पहले हटाने पड़ेंगे, फिर होगा आंसर. Okay. So the answer is, if I think of this edge case, the answer is, oh sorry, my bad. So the answer will be, first count the components, assume that to be x. Next, count the components, count the edges in the components which doesn't have one cycle, doesn't have any cycle, which means even if you remove one edge, it gives you one new component. Okay, and assume those number of edges are a. Required component is equal to k. So if you require it k, so if this a is somewhere greater than equal to k minus x, then your answer is always a, right? That's the first case. So basically I'm saying any of the component where there is no cycle, any of the edges on removal will give me one more component. So a is those number of edges where there are no cycles. So if you just remove them, you get one more component, you get one more component. So if the number of new more components, which is k minus x, if you have those many edges, the answer is always a. Okay, and there's another case that we have to deal with. What if a is lesser than k minus x? That means we don't have those many required things. This is where the problem starts getting complicated. This is where what you have to do is remove the cyclic. So what we have to do is we have to kind of remove the cyclic stuffs. So remove the cycles. So what's going to be my priority? My priority will be to remove those, like my priority will be to remove those edges, like the minimum edges, so that I can remove the cyclic thing. Like remove the edges from that component which has minimum edges that lead to a cycle. I can say that, right? Like that is what I'll try to do. Remove the edges from the component which has minimum edges that lead to a cycle. And once I've done that, I get more number of edges which can be freed. So I can go ahead and remove them as well, right? So I'll keep on doing this greedy algorithm. So the first thing, how do I figure out cycle or not? I think I can use something as the disjoint set algorithm, which is the DSU one. I'll use the DSU, which will keep telling me if two edges form a cycle or not, if two edges are a part of the same component or not. I'll use the DSUs. So there are a couple of like functions of union, where edges will get combined into the graph. There is find parent, which is going to tell me if they belong to the same component. So I'll be using these couple of functions. And since you asked about the time complexity, union takes around 4 alpha, and find parent also takes around 4 alpha, which is as good as constant. So we can say that the union operation works like for us attaching edges in probably constant time, and even the find parent will work in similar constant time. So depending on the number of edges you are giving, that's if the number of edges is m, I will be ending up taking big of m time to find out the answer. That's what my perception is.
Can you take a few examples to make sure that your algo is working?
Sure.
Like, yeah.
So what I'll okay, this doesn't go up. My bad. Okay, so let's go this up and go here. So what I'll do is, let's see this 1, 2, 3 and 1. Okay, so and let's take 4, 5, 6. Okay, and let's take 7, 8, 9. 7, 8, 9 connected to 10. Okay, connected to 10, connected to 7, back. So it forms a cycle, and I say 7 and 9 is also connected. Okay, so it's like 1, 2, 3 and 1. So it's a triangle. 4, 5, 6 are individuals. 7, 8, 9, 10, 7, 9 is kind of, if I have to show it properly, I'll show it. 7, 8, 9, 10. So it's probably something like this. If you can see this, it's probably something like this, right?
Yeah. Good.
I'm not sure if it's visible. Yeah, it's visible on my camera as well. So yeah, it's something like this. So at present, I have 3 components, correct? Imagine you have to form. Let's take a good number so that we can cover up the edge case. So currently we have 3 components. As you want to make 7. Let's try to make 7 components. So what's my first thing? I'll try to break down this edge. Broken, right? So 1 added to the answer. The next will be, let's break it down. So to remember this, please remember there were previously 3 components, right? And now I've broken down 1 more edge, so I got 1 more component. And I've broken 1 more edge, so I get 1 more component. And that's like 1, 2, 3, 4, and 5 components currently we have. We still require 7, correct? We still require 7. So let's understand, even if you remove this, it's still a cycle. So you're not forming any new components. So we somehow have to get rid of the cycle. So over here, we need to remove just 1 edge. If I'm correct, we have to just remove 1 edge because it's a triangle. So if you remove 1 edge, everything will become non-cyclic, correct? Because it's a triangle.
Okay.
And over here, you have to end up removing 2 edges, correct? Because it's a square, as I showed you. It's a square. Again, the opacity is very high.
Diagonal.
Yeah, there's a diagonal. So even if you remove 1 edge, you will not end up. So you have to end up removing 2 edges in order to get rid of the cyclic thing. So my preference will definitely be to go ahead and try to do something with this. So I'll add up 1 more to the answer and I'll remove probably this edge. Got it? So now I've got rid of the cyclic. Once I've got rid of the cyclic, I know one thing for sure, that over here, if I go ahead and remove 1, I get 1 more component, correct? So it's like 1 more removal. So it's like, okay, 1 component, 2 component, 3 component, 4 component, 5 component, 6 component. I still need 1 more. So I'll go ahead and remove this, which will give me exactly 7 components what were required. So it's like 3 plus 1, 4 plus 1, 5 plus 1, 6, 7, 8 edges removal, where 1 edge was crucial for getting rid of the cycle, right? So I required exactly removal of, I think, 1 edge. So these are the number of edges that I have to remove. Not 3 was the component. So 4 and 5 was the edge that I had removed. 5 and 6 was the edge that I've removed. There was 1 and 3 that I removed to get rid of the cycle.
I have a question.
Sure.
In the example that you took, you had 3 components. In the first one, there was 1 edge that you had to remove to make sure it is not cyclic. In the second one, there was no such edge. In the third one, there were 2 such edges, right? Since you have to find the minimum number of edges, so how many ever components are there? Are you also keeping track of like minimum number of edges that have to be removed to
Yeah, that's what will happen, na, right? If you know which component has minimum number of edges to remove to get a cycle. So to remove the cycle,
so
you have to keep a track of that. Yeah. And disjoint set will help you to do it, because when you're trying to connect it, when you try to connect 7 and 8, you know they belong to different. So that's not an extra edge. 8 and 9 connected, not an extra. 9 and 10 connected, not an extra. 10 and 7 connected, yeah, that's a cycle. So it's an extra edge which is causing the cycle. So 1 edge, 10 and 9 connected, 1 edge. So first you can go ahead and probably put everything down, and then you can do 1 more iteration to figure out which edges are extra and store it accordingly. Yeah, that's how I'll plan to do it.
If you're confident about it, let's get started with the code, because
the algorithm looks good, right?
Yeah.
Cool. So I need to code it. Since I require a disjoint set union, so do I need to code the DSU completely? So what I'll do is I'll probably create a class.
You can leave. Yeah.
Do I need to code it, or should I leave it?
You can leave it for now. If we have time, we can see later.
Okay, so assuming as all of us know that union, it usually takes couple of couple of things, couple of nodes, and tries to connect them. And there is something as find parent, which does it recursively. So if you give U, it tells you basically the parent which is same for a component. So these are the two ones. We can code it afterwards, and both of them will be working in Pico of 4 alpha time complexity. Cool. So now I'll go ahead and try to code it. So I'm assuming, since you've said you'll be giving n nodes, m edges, so vector, and you require the answer minimum, right? So minimum edges, and n you have given, m you have given, and I'm assuming you're giving, I'm not sure if weight has any significance. I don't think weight has any significance to the problem. So do we include weight?
You can remove it for now.
Yeah, then what I'll do is I'll just have this thing, okay, which basically gives me all the edges. Simple as that. So what I've done is I've tried to just take n and m and take the pair of edges. Simple as that.
Okay.
So at first what I'll try to do is I'll try to put everything, try to connect them, like from the graph using DSU. That's my first thing that I'll do. So I'll create an object. I hope I've not forgotten C++ because it's been super long. I've coded in C++ specifically for interview, but yeah, DSU. So I've created an object of it, and next what I'll do is I'll work through all the edges, and I know this is the U, this is the V. So these are the couple of nodes that you have to connect. So I'll just go ahead and say DSU dot union, and I'll just go ahead and connect it. That's the first thing that I will do. Next, I need the number of components. So assume X, or in order to have a better naming, current components is equal to 0. That is what I've kept. And now I'll go ahead and say how many, like, DSU works in such a way that one of them will have the parent pointing to himself. So I can easily figure out the number of, assuming, again, a quick question. I'm just considering that the graph is 1 based indexing. Does that work?
Yeah.
Okay. So I'll go ahead and I'll be like, if DSU dot find parent of I is equal to I can say current components plus plus. That's what I will do. So this will end up counting my current components. Okay, so basically anyone pointing to itself will count me the number of current components. New required is like more required rather. That's a better variable name. That will be K. Okay, forgot to take K. So K is what you require. So K minus current components is what you'll be requiring more. Now it's time to figure out the number of edges. Those are independent, like they kind of don't, they're not a part of these cyclic things. Okay, so how can we do it? That's a good question. So what I'll do is I'll reiterate through the edges and I'll figure out which components don't have a cycle and which components have a cycle. Let's try to do it. So what I can do is, since I need to store the component numbers, so let's say no cycle. So this list will store all the components with no cycle, and there will be another list which will store all the things with the cycle. And let's go across the edges again. And okay, and
so no cycle and cycle is like no cycle. So that is one, like
list.
one component, or
One list which is going to store all the parents of the components. Parents, which will store, basically say this component's parent has no cycle. So, and I'll use something as visited, which tells me, okay, do I need a no cycle or no cycle? Let me think on this. Maybe I'll use a visited. There's so many things to cover. Or I'll probably think it while implementing it. What can be the better solution? But as of now, I'll just try to keep it of this sort. Cycle. Okay, and now, okay, I need to see if there's a cycle. So I'm assuming initially, okay, can I just say, okay, let's do one thing. So initially I'm assuming everyone doesn't have a cycle. That's what I'll say initially. Now I'll say find parent, which is rather dsu dot find parent it dot first. If that's equal to find parent it dot second, that means that will be always the case. How do I figure out that it's a cycle? That's a good one. Okay, how do I figure out that it's a part of the cycle? Because they're already connected. And while I'm doing a union, this is where the edges went. Okay. So what I'll do is, I'll start a pair over here, which will be the cyclic edges. Yeah, nice. I can store all the cyclic edges over here. So instead of doing the union, I'll be like, hey, listen, dsu dot find pair u, is that equivalent to dsu find pair? So that means if the parents are already equal, that means these edges are already connected, and that can only happen if they're part of a cycle. And now I'll store them in a cyclic edges. So what I've done is I've stored all the edges that contribute to a cycle in a component. Okay. So I'll go ahead.
Every time you're doing a union, you are adding that into cycle.
No, before doing a union, I'm checking if there's a parent. And if it's not, then I'll go ahead and do the union. Okay. Okay, U and B. Perfect. So if the parent is same, I say they are the cyclic edges. Okay, this counts the current components. I have all the cyclic edges. What's the next thing that I have to do? Cyclic edges. Okay, so let's mark down all the components which are cyclic, all the parents that are cyclic. So what I'll do is I will go ahead to the cyclic edges, and when I go across the cyclic edges, I will say if, so I have to mark it, cycle dsu dot find parent it dot first, because that's a cyclic edge. So I say, give me a parent, and I go across and say, please mark it. So this guy has a cycle. Okay, perfect. So went across all the cyclic edges and marked it, saying these components have cyclic edges. Done. What's the next thing that I have to do?
Can you explain what you did over here?
This one? So what I did was I went through all the cyclic edges, and then I went to this particular cycle where I'm stating which nodes are part of a cyclic component. Correct? So
okay.
I'll just keep a track. I'll just keep a track of which parents are cycle, like have a cycle in it. So this will make sure, because since I stored all the cyclic edges, finding their parent and marking them, one will say, okay, these people have it. That's how it works.
But you don't care about how many edges are contributing to cycles? Like in the example that we had taken, they were like 1 and 2 edges, right?
Yeah, we can easily find it using the cyclic edges thing, because since I'm storing all the cyclic edges, it will be super easy to find it. So what you can do is probably, like, since you said about this, maybe we can compute it now, or as we go forward we can, if we require it, because I was thinking that, like, I'll only compute it if it is required, so that it doesn't add up to the time complexity. So currently I am storing all the cycles. Now it's time to figure out all the edges that are not part of cyclic components. So if you remember, we took it as A, correct? So what I'll do is I'll go through all the edges again. It's a complicated solution, too big. So this time what I'll do is I'll say dsu dot find parent. No, I just need to check if it's a cycle. Are you a part of cycle? So dsu dot find parent, are you a part of cycle? So if this guy is not a part of cycle, which means the cycle will be 0, I'll just keep on counting. Done. So what I've done is I've counted down all the edges which are not a part of cyclic components. So I have a count of all the edges, and I know one thing: if A is greater than equal to the required components. If you remember, this was it. The answer will be more required, because I'll just remove parts of those A, right? Okay, so this is done. Now, my next job is I need to figure out how many more we need, right? And that is where the complication starts. Because till here it was pretty easy. Like, I just went ahead, created the graph, counted the current components, figured out how many more are required, and figured out how many edges are not a part of the cyclic components. And then this was it. Now the main thing starts. How many more we require? Cyclic mode removal, maybe something like this. And that will be nothing but more required, because one thing I'm sure is I'll always remove A. No matter what A is, I'll remove all the single guys. So going back to this example, if you remember, I removed everything from 4, 5, 6. So I will go ahead and remove everything from this thing. And then I need to remove something so that I get back to the same thing. Now, this is where I have to start thinking, how do I make sure that I remove the correct ones? No matter what A is, I'll remove all the single guys. So going back to this example, if you remember, I removed everything from 4, 5, 6. So I will go ahead and remove everything from this thing. And then I need to remove something so that I get back to the same thing. Now, this is where I have to start thinking, how do I make sure that I remove the correct ones? Okay, let's count it, as you said. So let's probably keep a vector which will count the edges responsible for cycles, and maybe name it as n+1 and 0 initially. And now let's go ahead. If you remember, we stored all the cyclic edges.
Mm-hmm. If you don't mind, can you also write what A means over there? So, like,
Sure.
for audience when
Sure. Stores the rather count. That on removal. Okay, separate compose. So let me think now. We have a cyclic edge. You are in U and V. Now they belong to a parent for sure. So I will say count edges responsible for cycle. And I will say DSU, whoever is the parent, please go ahead and on it do a ++. So I know for every parent how many are there, correct? This is something we know for sure. And the other thing that I have to do is I have to also keep a track of the other components. Okay, how do I make sure that I do it in the best time complexity? Count edges responsible for cycles. This is done. Now I have to remove them. That's the first thing. The priority should be removal of the lesser appointed guys. Okay. And then the priority should be to remove those people who are not a part of it. Okay. Okay, got it. Perfect. Let's also count the edges per component. I know I'm taking a lot of if and buts, but that's to minimize the time complexity. Edges per component. For this, what I'll do is edges per component. For this, I can just go ahead and just iterate on the edges. I can do edges per component DSU dot find parent. So what I did was over here, I just went ahead and for every component, I asked them how many edges are there. If you remember the square, if you remember there were 4 and there was a diagonal 5. So this will keep the count as 5. Okay, edges per component. Now we have to start thinking. Count edges responsible for cycles. Okay, so we know.
I have a question.
Sure.
Like, is it like the very easy thing would be if you have edges per component, you just need like number of edges in the component without cycles should be, so if there are n edges in the component, it should be n-1, right?
n edges in
So
the
it will be
component.
very-
Sorry, I did not get it.
So if there is no cycle, if there are like 4 nodes, then without any cycle there should be 3, but there were 5. You know that. So you just have to remove 2. Isn't it very easy that way?
Yeah, that's what I'm thinking. Okay, so you're saying if there are 4 nodes in the component and there are 5 edges, the number of
You know that it should be n minus 1.
in order to get all the answers, correct?
But it will not always be the case. There can be edge cases, obviously, because if there are more cycles.
Yeah, I think that will not be the case, because what if 8 and 10 are connected? Then
Okay, it's better to go ahead like
yeah,
this.
because greedily what we have to think is, on a cyclic component, the cyclic component who has the least removal, that's what I have to actually think. So that's why
Yeah.
it might be done in a easier way, but since it's a
Cool.
longer code, I might be missing. But yeah, okay, getting back to the code, long code, edges per component. So how much do I require more? That's where I have to do it. So now I think now what I have to do is I have to start greedily start from the compose, which has less removal of edges, correct? So what I have to do is, for this I have to just sort it, or maybe do something on this so that I go ahead on that. And what data structure can we use? Maybe set. No, not set, because set will do it. So what I need to store is unique parent and the count. Okay, what is the data structure that gives me? Okay, vector pair, cycle. So this will be cycle removal, and I need parent and her parent का कितना removal. Cycle removed, parent wise. So this can go as, okay, let's keep it as empty one initially. And now what I'll do is I'll go ahead here, which is again something like this. And now what I'll do is 18 minute ho gaya bhai sahab. Okay, now the next thing I'll do is for count edges responsible for cycle. Just a second. If I go ahead on this, I have to check, are you a part? Do you have a cycle? Okay. So do you have a cycle? The first thing I have to check. Do you have a cycle? If you have a cycle, okay, cool, come ahead and go into this. And while you go ahead into this, I say push back. What are the number of removals that you have to deal with? So go ahead, number of removals that you have to deal with, which is definitely this. And once you know the number of removals, you say dsu dot find parent, or rather the parent is I itself, I. So what I've done is I've stored the HS responsible that you have to remove and the parent of the component. So we will have everything. So if you sort this up, which is like sort cycle removal dot begin cycle removal dot end, what this will do is this will give you the least removal. Now I think it's an easier job. I think it becomes quite easy because we have the edges per component, we have how much we have to remove, and it's a simple job, because what I need is I need how much more I require. Cyclic more removal is what I require. So either we could go this way, or we can just go like this. Okay, what's the easiest way that we can do it? The easiest way is, okay, let's maybe just go ahead this one, which is going ahead on this one, and removals will be id dot first. This is what I require. Number of edges in that component is this, and the parent will be at id dot second. So number of edges per component will be parent. Okay, cool. So this is something which we know, and we knew one thing. The answer. So if you remember, we have to definitely remove it. That's for sure. We have to remove it. So the first thing that I'll do with this is we will end up removing the removals, because then the cycle is gone. Once we have ended up removing the removals, can I say the edges in that component will also reduce? I repeat, the edges in that component will also reduce by the removals, correct? Now what's the next thing that I'll do? I have added a plus equal to removals, which is the removal answered. Now I need to add minimum. How much is still left? Because the leftover, I know I've taken it over here. So just do this. Okay, so we need more required minus a. So that will be a minimum of either edges in that component which is still remaining, comma, the left. And left will be removed with these many edges. Okay, and if at any moment left goes below 0 or equal to, because if there are no left, I break out. Ah, nice. And return. The answer is A. So either you can store it, maybe you can keep it answer, and the return will be answer. Okay, yeah, done. So if I have to explain it, what I did was, I think, a pretty greedy approach. So I'll just quickly walk through the code, because I know it's a long code. So what I did was, I took the edges, I took the K, and I took N and M. I just kept a cyclic edges list, and I iterated through it. And if they belong to the same component, that means they are an edge which is creating a cycle, correct? So I put them across the cyclic edge list. Then I went across and I said, how many individual components are there? And that came up as current component. And how much more do I require? The current minus the requirement. And then I went over all the cyclic edges and I marked them. So I keep a track which components are responsible for cycles. Now I again go over, again, this probably could have been done in a much cleaner way. So again, go over the edges and I say, are you a cyclic component? If you are not, like this edge is not part of a cyclic component, I count all the edges that are not part of the cyclic component. And then if that's more than the more required, that's okay, fine. I just, that's my answer. And then the main thing starts, where I count the edges responsible for cycles and I count the edges per component. So for counting the edges per component, it's pretty simple. I iterate over the edges, and wherever they belong, the parent, I just keep on counting them. And then I go across the cyclic edges and I say, if like these are the cyclic edges responsible for this particular parent. So I keep a track of that. And then I just go ahead and say, okay, for every parent, how many cycles do you need to remove? Simple as that. And why do I do that? The reason I had to do it, because I had to sort it. So I tried to keep it in a pair. Probably can be done in a much better way if the code was shorter. And it was not an interview, definitely. So this is where I store everything in the cycle removed so that I can sort it. Once I've sorted it, greedily, I have the components which has the least removals. So I go through them, and it's a simple greedy approach. What I've done is, first I remove all the cycles in that, which is the removals, which will add up to the answer. Then I say, okay, those are removed from the component. So the number of edges remaining in that component is minus that. Then I add up the minimum and then I subtract it from the left. If at any moment I do not require any further left, that's perfect. If the left is still greater than 0 after all these doing, return -1. That's not possible. So that's the answer. Yeah, that's how the answer will be. I might have missed a lot of cases. I might have written a longer code, but yeah, that's the answer.
Can you quickly talk about the time complexity through the code? Like
Sure.
What is the time complexity of what part of the code? Yeah.
Sure, we have 25 minutes. Okay, so the time complexity, again, this is bgo of m for the edges. I'm assuming this to be constant, the find parent. Bgo of n again, cyclic edges, depending on how many cyclic edges you give me. So this can be a variable quantity, so we cannot specifically say about the time complexity of this one. Again, on this, it's a big O of m. This is again a big O of m. This is again depending a variable time complexity. So again, big O of n over here. And this is again depending on how many cycles you have. So I think we are using big O of n, I think 4 or 5 times. So we can trim it down to somewhere around 5n plus the variables like n log n. Again, this is how many cycles. These are all variable quantities, so I will not analyze this, because let's take x log x. So it's like 5n plus x log x, somewhere near about that. If we go on writing, we can find out the exact one. Yeah, and the space complexity, I think we're using cyclic edges, again variable one. We're using big of n here. Yeah, we're using near about big of 3 and 4n as the space complexity. Yeah, that's it.
Cool. Do you want to take quick 3-4 examples, or maybe 1 or 2 examples, and like see how the code is running?
Sure, I'll do that. Okay, since you said me to walk you over this particular code with an example, probably I think the best example that we took was this. So I'll take this. Right, this was the example, and I'll just omit this. So at first, what will happen is, with this, the cyclic edges will end up storing these things: 3, 1, correct, and then 10, 7, and then 7, 9. Perfect. This is what it will be stored as. And next, as you move forward, this current component will be ending up storing the value 3, right? Because there are 3 components, because it will just go through and find out. I'm not going through the deep in DSU, because this is definitely, it will take a lot of time. And then how many more are required? So since we took K as 7, the more required will be 4, correct? And now I'll go ahead and say, okay, let's mark all of the cyclic components, assuming the parents to be 1, 4, and 7. Assuming the parents to be 1, 4, and 7, the cycles will be marked as 1, 4, and 7. Like, these are the main parents which will be marked. Next, going across, stores the count of edges that on removal give 2 separate compos. So if the cycle is 0, then only I count it. So it will end up counting 4, 5, and 5, 6. So 2, right? Because everyone else is a part of cycle. So this, where A will be valued at 2, because everyone else is a part of cycle. Done. Since A is valued as 2, how many more did you require? If you remember, the more required was 4. So this if will never get executed. Now what I do is, as I say, count edges responsible for cycles and edges per component. Now I go across all the edges and I say edges per component. So what this will do is, remember, we are just counting it as find, like, at the parent. So if you remember, the parent was 1, the parent was 4, the parent was 7, right? So how many edges will 1 have? It will end up having 3 edges. 4 will end up having 2, and this will end up having 5. So 3, 2, 5. So this will have 3, this will have 2, 2, this will have 5, right? And this is done. Now what this will do is count edges responsible for cycles. So again, it will end up storing at 1, 4, and 7, because that is where DSU will make it store. For 1, can I say there is just 1 edge responsible for a cycle? Because cyclic edge, if you remember the cyclic edge we stored over here, so this will make sure that it will count it. So 1 will be storing 1, 4 will be storing 0, because there will be no 1, and 7 will be storing 2. Done? Yeah, perfect. And then I say cycle removed parent wise. So what I have done over here is, so I've just sorted it. So after sorting, it will look something like, the least removal will be at okay, so it is just storing the cycles 1. So the least removal will be with the 1. So it will be storing 1, 1 at the first, and then it will be storing 2, 7, because that's the next removal. Done? Okay.
What about
0,
4?
Cycle 1. You don't store anything apart from the cycles.
Yeah. Okay. Yeah.
Next, we say how many more are required. If you remember, the more required will be 4 minus 2, because there's 4 minus 2. So we require 2 more, right? So we go across and say how many removals. So this is iterating on this. The first time the removals will be called as 1. The parent will be called as 1. Edges in that component. How many edges were there in the component? 1, 2, 3. Let's go. 3. And we've already stored it. So the edges in the component will be 3. Plus removals. So the answer, which as of now is stored as 2 because that's what you remove. So this will be adding plus removals, the cycle removals, which is 1. Added. So the answer will be added to 2 plus 1, 3. And the component edges, which is 3, will get removed. So how many edges are there removed? Are they left? 2. And I say min. How many more do I require? The more requirement was 2, if I'm not wrong. Correct? The more was it 2? It was 2. So I say min edges in that component. 2 left over 2. So the answer will end up taking another 2, which is okay. Right? And then leftover is lesser than 0. So it breaks out and it returns the answer. And if you go back and see over here, does that add up to the answer? Okay, so if I remove this, perfect. If I remove this, if I remove this, if I remove this, if I remove this, do I get 7 components? We do 1, 6, 3 and 3, 6. So 3 plus 3, 6 and 1 component, 7, and we reach it. So
congratulations.
Yeah, and that's how I just wrote this one so that we don't end up getting over this because there's no point in removing this. That's why, and the minimum was written because in case there are a lot of edges in that component, but I just have little bit of requirements, so that's why the minimum was written. So yeah, that was it. I'm sure there might be a better solution. This is what I did come up.
There are a lot of possible solutions for the same question, but then being able to write so much of code in 45 minutes is a huge deal. You can have some water now.
Yeah, I think like the thing with these questions is a lot of people do ask me, what if I haven't seen the question beforehand? So I did not see that question beforehand. Yeah, had I seen this question, I would have known what algorithm to use. So I'll say in an interview, I think even if you haven't seen the solution, it's about just finding out something. You have to find out a way. If I remember my media.net interview, it went up to 1 hour or 10 minutes. I gave him a weird solution. And the only reason he was happy was I did not give up. And I ended up writing something. And somewhere, maybe, I'm sure maybe it was not the correct solution, but I was happy that I was trying. I was thinking of every corner. I think that's important.
Right. So I guess we'll also have to run through all the edge cases to make sure that this is working, but it is a very good solution, of course. So thank you so much for taking out time and doing this. So many people look up to you. You have like millions of views on your graph series. I'm sure like people are going to be very intrigued watching the master really solve the question. One good point to take away from this is that, even though you teach all the time, it is harder to get back to an interview. It is never easy for an interview, right? People give up so easily. They think that they should be able to do so good an interview. That is not the case because interviews pressure and the time limit and everything is so much worse. So even though we have regular practice, we have to really prepare for this. So could you talk about this a bit? How was it being in a mock interview?
Yeah, I think when you texted me up the last week and we had a discussion, I think I was very afraid that I might not be able to solve. And people think कि यार ये पढ़ाता है तो he will solve. That's not the case because for an interview, you have to go through all the algorithms. You have to have DSU and everything on your hands. No matter how much you teach, you have to go through that entire wind. And I'm not sure where you got this question from. It's definitely not a 45-minute interview question. And
I had to get the toughest question. It was for you. Otherwise, people would have to 𝐶hIVA can easily solve this. So I had to get a very hard question.
Yeah, it is. I think it is a hard question, and I honestly don't expect this question to come up in an interview. And again, the solution that I gave might be messing up cases. But when you get into an interview, it's not about solving a problem. That is what I've understood with all my experience in the industry. In an interview, if people are coming up with hard questions, it's about to see how does this guy approach? Does he gives up? Because I've seen a lot of people nowadays, the cramming up has started. They cram up solutions. कि Dijkstra है, चलो Dijkstra पढ़ लिया, DSU है पढ़ लिया, वही आया तो मैं कर लूँगा. तो I think cramming up is not the solution. अगर आपको एक ऐसा unknown question, because this was an unknown question, I hadn't seen it, and when you come up with unknown questions, it's just about giving up what you have, whatever your brain can think of. That's it. ठीक है, like in that 45 minutes, it's not easy to come up with the exact solution. And maybe if I was in practice, I would have come up with something. This is the CP in me which came up. That's why I ended up writing such a long code. But yeah, the only tip that I'll give to everyone watching is just go through the interviews. Don't think that you have to give the perfect solution. It's not the perfect. No one is perfect. No one can give a perfect solution. Just show what you have, what you can think of, what you can write of. Just show your skills. They will not reject you if you don't come up with the 100% correct solution. Then look up on a lot of other factors which Keerti can maybe आप बोल सकते हो.
Yeah. Like there were a lot of tips during the interview also that they were able to see. So just keep that in mind that, you don't have to be really perfect in any interview, but don't give up just because you think that this is not going to work out. So, and don't expect you to be like really awesome and you're going to remember. I hear a lot of people complaining that we forgot the concepts after 6 months. It will take you a week to just brush up the concepts. Once you've understood it, it will be easier for you to brush it up. Just that don't give up. Like like people start blaming themselves like, we are not smart enough, we keep forgetting it. But everyone forgets. Everyone forgets. We do have to prepare again right before the end.
True.
Yep. Thank you so much for making time for this. Like, this was awesome. Thank you. I have been waiting for this like since so long. Finally, it happened.
Yeah, thank you so much for having me. And yeah, do like, share, and subscribe. And with this, shall we wrap up?
Yeah. Thank you.
See ya. Bye bye.